maybe a little bit more straightforward way of talking about a microstate. So this is an example that I use in general chemistry. So suppose we have this four molecules in a two bulb flask. Okay, so we can say confidently here that N and V are fixed. So we're talking about four volumes. We're not going to change the volume of the flask. We're saying it's a two volume flask. And then also we're going to hold temperature constant. Okay, so we're working in the canonical ensemble. N, V, and T are all set to give us the macro state. Okay, and the macro state is just simply four molecules in a two bulb flask at some temperature. That's it. That's the macro state. What are the resulting number of microstates? Okay. Well, if you start thinking about how we could arrange this, so we could have all four particles in the left bulb, and that would correspond to one microstate. That's one arrangement that doesn't affect the total energy of the system. But now if I start putting labels on those four molecules, I label them molecule A, B, C, and D. And I accept that, okay, well now one arrangement will be three molecules on the left and one molecule on the right. However, because I've labeled them, there's now four different ways that I could do that. For example, I could have only A on the right flask and B, D, and C on the left flask. I could now exchange A and B, or I could exchange B and C, or I could exchange D and C. That would give me four microstates because none of those would directly change the energy of this system. All right? And if I kept going through all of these possibilities, I would have 1 plus 4 plus 6 plus 4 plus 1. So what is that? 5, 11, 16 microstates would result from this one macrostate. Okay? So we might imagine as we make this macrostate more complicated, so maybe instead of only four bulbs, what if it, or excuse me, instead of four molecules, what if it was 1 mole of molecules? We would have a hideous, disgusting number of microstates. Way too many to count. Absolutely way too many to count. So how could we then calculate those number of microstates? Well, one way would be to use the molecular partition function. Okay, we could do that. That partition function would help us sum all of those possible states. Another way would be to use the Boltzmann definition of entropy, which states S equals KB, K Boltzmann, times natural log, times W. So here in this equation, W is typically used to represent that number of microstates. Okay, so instead of counting those number of microstates, you could then determine the entropy instead, and that would tell you how many microstates you have. Okay, so of course this would give us, K Boltzmann if we were talking about molecular units, right? Because we know K Boltzmann is joule per molecule per Kelvin. We know if we were talking about mole units, we could write S is R times natural log of the number of microstates. Okay, and really instead of thinking about the number of microstates as this way of arranging things, a better way to think of that is the entropy. So we often think of entropy definition as like, the order or disorder, right? You commonly hear entropy as like a measure of chaos. Well, this is where that comes from. Because, right, with a large number of microstates, entropy will go up, and it will go up in this exponential way. Okay? Another way to think of this is, suppose we only had one microstate. Okay? Then what's our entropy? Natural log of 1, let's just double check in case we've all forgot. 1 natural log, natural log of 1 is 0, right? So if we only had one singular way to arrange our system, it has, by definition, no entropy. So start conceptualizing this thing between entropy and number of microstates. So entropy is not really a measure of chaos. It's really a measure of the number of ways we can arrange things without changing the energy. Okay? So, and now this other formula that I put here, I'm not going to derive this, but this is how you could actually connect entropy as a function of temperature to that canonical, assuming I can spell, that canonical partition function. So that's what that Q is. So they're related, microstates and the partition functions. I'm not going to show how this is derived, and I'm not concerned with that. That you know how, you can look that up in chapter 15 if you're curious. But what this equation gives you is, so that's, you know, internal energy, right? Internal energy as a function of temperature. So whatever this temperature is, that temperature matches it. And as you might guess, at 0 Kelvin, this equation will just give you S of 0 is KB times natural log of Q, the partition function. So at T equals 0, I'm not going to show this, but we did talk about this earlier. Q is going to equal 1, okay? And so then we would arrive at this same conclusion that at 0 Kelvin, we only have one singular way to arrange a system, and thus it's 0 entropy. Okay. So here is Boltzmann's tombstone. Famously, he has his equation K log W. So you know, now we use the base E natural log. Here was the base 10, but very famous. It's really cool that he's got his equation on his tombstone right there. So really neat. Okay, continuing along.